Okay, so like Mario said, my name is Michael Kane. Today I'm going to be talking about, I'm actually going to be talking about a communication framework that I've been working on for a little while. I'll get to the distributed data structures, essentially, that are built on top of the communication framework that I'm going to talk about. So since this is kind of a smaller group, or I mean, I mean that I'm not on a microphone or anything, and I'm not really into into waiting till the impulse control. So if people have questions, you can ask them immediately. Just yell them out, and I'll try to answer them. If you're a muckraker, go right ahead, please. I think it makes for much better talks. So first, a word from my sponsors. So first, just as an acknowledgement, some of the work that I'm going to show was actually done by Simon Urbanik, who's part of the R Core. He's at AT&T Labs Research, and that was actually to get some of I needed some asynchronous functionality in R. I'll talk about that in a little bit, and I'll clearly identify the stuff that he did. The other thing is part of the research that's being presented is part of the XData program, which is part of the White House's Big Data Initiative. There's a disclaimer also. All right, so to begin with, so one other thing is, I wanted to, just as a poll, how many people are R programmers here? All right, is it mostly Python programmers? All right, some Python programmers. And Java programmers? All right, so more Java programmers. All right, so the Hadoop crowd has come to beat me up, maybe. All right, so almost nothing that I'm going to present here is really R specific. It's more the design. I'll show a little bit of R code, but it's pretty straightforward. If somebody has a question about that, again, please don't hesitate to ask. So I'm going to start with what I was calling deconstructing distributed computing. So I wanted to start, I wanted to just think about what are kind of the essential elements for doing distributed computing. And so I'm going to use a little bit different nomenclature. I'm going to use coordinator for, if you're from the MPI world, this would be a master. But I say coordinator because I want it to mean something a little bit different. And then the workers. So what usually happens is you have, and this is for dynamic languages or interpretive languages. Usually you start out with a set of expressions on the coordinator. So the coordinator is going to be the process that creates these expressions that should be executed out in the cluster. After that, the expressions are moved to parallel processes. They're evaluated. And sometimes the results of those evaluations need to be moved around between the workers. So I'm not just thinking about about embarrassingly parallel computations. I really want to think about distributed computing in full generality. Data can be moving all around the cluster. And then then they go back to the coordinator usually. And then it's some result is returned to the coordinator. So just in terms of essential components, we have the coordinator that describes the computation that's supposed to happen out on the cluster. We have the workers that evaluate the expressions. You need some mechanism for getting the data from the coordinator to the workers. You need some other mechanism that gets data between workers, and then some other mechanism that gets a result back to the coordinator. So when we talk about distributed computing, we're really talking about distributed communication protocols. The actual evaluation is pretty simple. Whether you're Python, Java, or R, you're really just getting an expression and you're calling eval on it. So in terms of the existing communication protocols, The big one has been traditionally MPI, right? So you have, so the model for MPI is you essentially define all of the data movement up front, and then the workers end up communicating directly, or can communicate directly through each other through these things called mailboxes. The cool thing about MPI is the performance is really good. It's probably, yeah, out of most, yeah, it's if you compare it to most of the other distributed computing platforms, its performance is usually the best. The problem is it's not very fault tolerant. And the reason is because you are describing all of the data movement up front. If one of the machines goes down in the middle of a computation, then you have this problem where that description is no longer valid for the computation that you want to execute. So I've mostly seen this in R. The other way that we can do distributed computing, and again, I think I don't know of a lot of cases where. So I've only seen it recently. I haven't seen really much older cases, but using a configuration service. So in particular, I like Redis. So Redis is a key value database, and I have example R code. Basically, you have a coordinator. If the coordinator wants, he can do a push onto. Redis has this notion of lists. They can also act as queues. So I can do a push of hello worker session, and then I can turn around and do a blocking pop on a different list called the coordinator queue. Now this will actually block until it gets something back. So I can give it yeah. So this won't happen until somebody puts something in the coordinator queue, which is exactly what I'm showing here. With this, we're doing Redis Connect. We're popping something that was pushed. We see that it's hello worker session, and then I'm gonna push hello coordinator session back. So this is no surprise if you're a big Redis person. In fact, if you are a big Redis person, you may be thinking, who cares and why are you showing this to me? But it turns out this is actually a really nice model, especially for doing embarrassing and parallel computations. You have the coordinator, and you have the coordinator, which is whose job is to push things onto expressions to evaluate onto a queue, and then you have workers that are basically just sitting there blocked, waiting for something to happen. So in this case, as an example, let's say that 2 expressions come in. This means that 2 of the workers get jobs to do. They're gonna do evaluations and then push their results into a return queue, while this other worker who didn't get a job is still just waiting for things to do. So the really nice thing about this is it buys us this notion of communication orthogonality, which basically means that the no 2 nodes in the network really know about each other, but they can still communicate. It's actually it's a little bit formal than that, and it really means that 2 nodes in the network know a minimal amount of information to communicate. The problem is that by doing this, we're essentially centralizing data movement. Now, in this case, it wasn't as big a deal because all of the data is going back to the coordinator. But if we do run into a case where workers need to start talking to each other, that would mean we need new queues, which means more use of Redis. And if there's a lot of communication between the workers, then Redis essentially becomes the bottleneck. So I'm seeing nods, but not a lot of assertions. Is this? Do people already know about this, or not too much? I guess that's not a well-posed question for a poll. And people on the internet, I don't know what they think. All right. All right, so again, with MPI, you get really good performance, and you get these really nice peer-to-peer connections. With a system, with a piece of software like Redis, you get communication orthogonality, which essentially gives you elasticity. So let me back up. One of the nice things about this is because the coordinator and the workers aren't directly tied, I can add workers to my task queue at any time, right? So I can scale out really easily. At the same time, if I want to, I can start removing workers, and then if I add a little bit more accounting, the coordinator can detect when a task has been pushed through and times out essentially, in which case you can resubmit the task. So those are the two parts you need for elasticity, right? You need the fault tolerance part, and then you need to be able to scale up and make use of available resources as they become available. So again, MPI is fast peer-to-peer connections. Redis is elastic. So the idea is, can we kind of build a communication framework that takes the best of both these things and allows an elastic communication framework that also lets us do peer-to-peer connections. So I have this package of, the name is actually, it's called Nadaria. The C is silent. And people always ask, well, how do I pronounce that? And then they ask, well, why did you pick that name? It was basically that I didn't want anything that had to do at all with an elephant. The other thing was, I was originally thinking of, I wanted something that encapsulated this idea of regeneration. And I started by looking at, I was thinking about Hydra. The problem with that is it seemed a little like early 2000 or 1990s. Remember, like, we used to pick names for things that were really like aggressive, like, Kerberos and Cerberus, which were, the three-headed dog that guarded Hades. So I went back and looked up Hydra, and Hydra belongs to this phylum of organisms called the Nadaria. And I liked it. It also sounded like this magical place where all your distributed computing just kind of works. So that is the background of that. So I'm just going to show basically how it works. So I'm still going to use Redis, or key value database, as a queue, but we can think of it as I can submit a job, and in this case, this is C, A matrix multiply B. That is matrix multiply R. We have this goofy thing with putting percent around things. Now, in this case, this computation involves A. So I'm going to actually tell it to go to A. So this A, yeah. So this is N. So you can think of this as a matrix A, matrix B, and we want to do a matrix product and get C. So A gets the job, realizes it doesn't have B, and it also, we're still in the regime where the workers don't actually know about each other. So rather than trying to figure out where the worker is, he puts in a job back into Redis that says, basically says, send a job to B, and the job is essentially send me your B matrix. The way this is actually implemented is I'm using 0MQ, so what's actually put out is the resource that's needed along with the 0MQ endpoint. And so what happens then is A submits the job and then just waits to get the actual value. So B consumes this and says, all right, I need to send the data. Sends the data. The matrix multiply is performed. And then the thing that's returned is I have a choice. Either I can actually send the C matrix back, or I can say that or I can tell, I can send a message saying C is now available out on the cluster.
But
Yeah.
So actual computation is happening on the single node, right?
Yes. Yeah. Yeah, that's correct. So, right, so I'm thinking about matrix blocks here. And this is actually sufficient if I want to do a block-wise matrix multiply. So this is kind of the essential component. And I am much more interested in kind of the numerical linear algebra routines. Because I think the MapReduce, the traditional MapReduce things they're done now. You know, we do them well, especially the Java people.
How do you know where B is?
How do I know where?
How does A know where B is?
So, so the way that I'm doing is each one of these resources listens on a queue with its resource name. So A listens on a queue in Redis called A. So I kind of glossed over that. That's a good point, though. Now, what that does is it not only lets me localize the computation, but it lets me localize clusters, or I can kind of group things however I want by creating new queues for these workers to listen on.
So when you this thing on, it had A first, and so A was listening to it, so it picked up that.
Yes. Yes. Yeah. Exactly. All right, so that was, so pictures are nice, and they're good for us to convince, that things are working. But how is this actually used? So how do you program this? So this is where there's actually going to be a little bar code. So there are only two functions that you need to know about. If you want to use this, they're pull and push. Essentially, the idea is if you're doing a pull, you're giving the cluster an expression that it's going to then pull from, where it's going to pull the result of the expression. With a push, you're giving an expression to consume, and then whatever that resource is, whatever the result is going to stay out on the cluster, and you're going to get a handle to it. So the arguments are where you want the thing to, where you want the expression to be evaluated in terms of the queues, either the resource location or some other resource naming that you decided on. The expression, a broadcast. So should the expression go out to all of the resources that are serving, or all of the processes that are serving a resource? And then if you're doing a push, you may want to actually name the resource. Otherwise, we're just going to give it a global unique identifier. So if I want to do the example that I just showed, where we're creating a C out on the cluster, can be done with this expression. So it's essentially saying, go to wherever B is. Wherever B is, take B and multiply it by the thing that's returned by this. And the thing that's returned by this is A, is that A matrix. So we're pulling A onto B, doing the matrix multiply, and then since this is a push, I can name the resource and I want to call it C. So this is a little bit confusing because there's pulls and pushes. Does this make sense? The
way you showed was push A and pull B, right?
I showed push.
Went to A first.
Yeah, B is coming to A.
Oh yes, you know what? You're totally right. Yes, that's my mistake. That should be. You're right. That should be A. In which case, I should be pulling B. Yes. Yeah. So it was so confusing. I didn't even get it right. Yeah.
If you have a few workers that know about B, and one of them has A and B, does your job get scheduled on the one that has both?
Not by default. What you could do is you could tell the worker,
We have to have an AD key.
yes, yeah, yes. Yep.
So if A needs B, right, and B dies, what happens?
In this case, it'll time out. If you're in a regime where you're worried about machines going down, then what you would do is start serving blocks redundantly. Because that way, if one of them went down, if one of the machines went down with the resource that you're interested in, or where the resource is actually, where the computation is taking place, then what happens is that computation times out. The coordinator essentially sees that the computation is timed out and can resubmit. If all the blocks are being served redundantly, then the computation can still take place, albeit on different machines.
Question: what do you predict against the failure of the coordinator itself?
So how do I protect it from calling itself? So right. So are you worried about like an infinite recursion?
Actually, I'm asking how do you protect against the coordinator going down?
I don't. I don't right now. So yeah. So that's a good point. So there is potential for a fault there. You can, yeah, and without some kind of checkpointing for each one of the operations for the coordinator, that's yeah, that is tough to get around. The only thing is, no, that's right. Yeah, there's not a checkpoint for the coordinator, so it can go down. If it does go down, though, those resources still will exist out on the cluster. So if there's a record of the resources, they're still available if you were to restart the coordinator.
Is there any acknowledgement mechanism, like when you say, so suppose there are two workers pulling from the same on same like queue V, so which one gets which?
So it's with Redis, it's random essentially.
Oh, it's random.
Yes, yeah. So yes, so one of them will get it. Only one of them. Will get it.
Only one of them. Okay.
Yeah. So if you know about distributed computing in like the 80s, this may look a lot like tuple spaces, and in a lot of ways it is, and it does satisfy these four essential properties for a generative communication framework that David Galernger identified in a paper in 1985, which were space uncoupling, time uncoupling, distributed sharing, and support for continuation. I'm actually going to go through each one of those. But the punchline is that you can support a large class of communication patterns that you can with MPI. I'm not that you can't necessarily with MapReduce, with a lot of the MapReduce frameworks. So these four properties. The first one is space uncoupling, which basically means that a resource can be used by any member of the cluster. So once I do a push and a handle is returned, that's a handle for that resource. Anyone on the cluster can use it. So it can be pulled or involved in expressions. The time uncoupling means that the resource is there until it's explicitly removed. This is actually one of the places where I needed for a broadcast. So if I actually want to remove all instances of a resource on a cluster, I can just say on C, remove C, broadcast true. So that's going to go to anywhere that there's a resource C being served, it'll remove it. And I'm doing a pull, so nothing is being kept out on a cluster after the result. The distributed sharing. Right. So so this is saying that data can be shared across different R sessions. This is, yeah, so I already said that we can store resources redundantly. This is one of the things that lets us do kind of a multi-map compared to MapReduce. And if we want consistency, we actually do, that has consistency for data structures that has to be implemented as a policy, in other words, as a convention. The continuation passing, that's a little more of a technical term, but the big thing to realize about that is it's basically that you can have polls of polls or polls of pushes. Now, this is something that causes a lot of problems, or that originally caused a lot of problems in R, because R is single-threaded, right? So, so then there's the question of how do we actually handle deadlocking? And you want to see how you could cause a deadlock. It's essentially doing say go to A, then go to B, and try to pull A back to, A back to B. Because R is single-threaded, it would be blocking, waiting for B, and so this would not normally return. So to handle that, we essentially needed R to be able to work a little more like Node.js, where we needed to be able to essentially fork and kind of forget about a process, which didn't exist in R until version 3.1, and then we also needed to be able to fork and then change the state of the parent process. So when I first ran into this, I was shaking my fists thinking, oh, I should have done this in Python. And it turns out if you're nice to people in R core and you present things that they think are worthwhile, you can get certain functionality. So the first bit of functionality that Simon added was it's an enhancement to the mcparallel function. So for people that aren't R programmers, in R there's a function called mcparallel that essentially does a fork of the process. It executes an expression, and then you can read the result back. You can pull it. You can ask if it's ready. The problem with this is for a pull on a worker. Essentially, I didn't want to return anything. And if I didn't return anything in the old version of mcparallel, then I'd have pipes that essentially were not being cleaned up. So you get kind of a resource leak. So now there's this new option called detached. And you can think of, if you say detached equals true, you kind of fork and forget it. The R process does whatever it needs to, and you'll never hear about it again. This is exactly what I needed for my polls on the worker side, because essentially the worker gets a new expression, it's going to fork and then execute the expression. The fork process has the 0MQ endpoint, so if it needs to move things to so when it needs to move things to another worker or the coordinator, it just does that and then kills itself essentially. The other bit of functionality was for these pushes. Essentially, I needed to be able to change the state of the parent process of a worker based on a push. That's since after a push, the worker has a new is providing a new resource. Just forking or forgetting isn't good enough. You need to fork and then update the state of the parent. So the way that we can do that now is with the background package. If you're looking for it, it's not on CRAN, it's not on RForge. You have to go to rforge.net, which is Simon's package repository. And basically the idea is that you can give it an expression to execute, and then you can give it a callback. The callback is executed on the callback is executed after the result of the evaluation on the parent is or on the child is returned back to the parent. So for me, with the worker, I have a separate environment where I'm keeping all the resources that are being that are made available to the cluster, and basically the callback now updates that environment. Here's an example. If you want, again, it's on our forge.net. So the communication framework is okay, or is fine, but it's still very low level. And whenever we're doing data explorations, data analyses, we don't actually care about doing things like moving data from machine to machine. I don't even like writing MapReduce type things myself. I like to deal with really high level data structures. I like data frames. I like the way that we query it into them, whether it's with R or with the pandas package. So one of the things that I did was I followed, there are kind of conventions now for doing distributed data structures in R. And I think one of the best examples of this is in the SciDB R package from Brian Lewis. They have a couple of conventions. So basically the idea is a distributed data structure should look as much like an analogous local data structure as possible. That means that, you know, if the local data structure supports things like bracketing, the distributed thing should. It shouldn't be a function, or it shouldn't be a. If it's an operator locally, it should be an operator for the distributed thing. The other thing is in R. So any of the operations that you're doing should stay out on the cluster. You should not be bringing data into the coordinator, doing work, and then pushing it back out. But sometimes you need to move data onto the coordinator. So you can merge the data set with an open bracket, close bracket at the end of an expression. The nice thing about this in R is that we're not violating the convention. So in R, if you have, say, a vector and you index it, so you have v of 1 to 10, and then you do an open bracket, close bracket, it actually returns you the same vector as if you said v from 1 to 10. So we're not really imposing a new condition on how we manipulate distributed data structures. The other thing is you should, again, because you should always be able to bring the data back, but the data may be really big. You should be able to create an iterator to actually iterate through different chunks of the data and be able to handle it piecewise if you need to. So I actually have a couple of these data structures done now. The distributed vector turns out to be, if we think about how it's actually implemented in R, it's very simple, right? It's basically a C array. The nice thing about it is we can index it with other vectors. Now, because one of the things I really wanted to be able to do is index a distributed vector with another distributed vector. This is actually where a lot of my work went in. So basically, at this point, so right now, as it is right now, you can do things like you can create a distributed vector, and I'm just filling it. This is a relatively small distributed vector, right? It's only 1,000 values, and it's using chunk sizes of 79. So it's again, each one of the blocks is it's a vector of random normals of size 79. Then here I'm sampling from 1 to the length of the distributed vector. So that's sampling from 1 to 1,000. I'm sampling 35 values, and I'm creating block sizes. The block size is 14. So one of the really nice things about this is you can start mixing and matching block sizes. If you've done things with scalapack, you know that's not always that easy. It's also it's tricky with most distributed linear algebra systems. And then what you can do is I can actually index one distributed vector with another distributed vector. So all the data movement is handled, and it's indexed properly, and I can check that this works because I can check that this works by emerging DV onto the local machine, emerging IV onto the local machine, indexing local DV with local IV, and then make sure that it's equal to this expression that I had before emerged onto the local machine. So that's basically how I've been testing it. So why did I spend so much time on this, on the vectors? So it turns out anytime I want to do indexing or these logical expressions with data frames, we're always creating vectors, right? So once I can do this, and once I can do binary infix operators like or and, then I can start indexing distributed data frames. So the block model for a distributed data frame right now is that I'm assuming that it's a relatively small number of columns, and I'm taking blocks row-wise. The reason for that is I kind of decided that it was really wide, that you actually don't want a distributed data frame. I guess if people don't like it, they can write their own versions. But because I now have distributed vectors working correctly, I can get all this indexing functionality for a distributed data frame. I'm currently working on distributed matrices. This is actually the part that I'm the most excited about. We did some early tests with this, and again, because there's this brokering mechanism for any of the data movement, we don't expect to be as fast as MPI, right? And with MPI, all the data movement is already decided on up front. Because we're doing this brokering, we expect a little bit of a delay. It turns out that it's actually the benchmarks show for pretty small examples that they're really comparable. So we don't think we're losing too much with the brokering scheme. The other thing that we can do is, because these matrices are just R objects, and R knows how to multiply sparse and dense matrices, we don't have to distinguish between a dense distributed matrix and a sparse distributed matrix, which is also a big deal. So we can handle, you get a lot of these that are matrices that are clumping, especially if you're dealing with social network data. You get one or two people that are connected to everyone, and then other people that are connected to no one, and it can be difficult deciding if a sparse representation is correct or a dense representation. With something like this, we don't actually care. All we really end up doing is for again, because we're just moving R objects that we can multiply. And it's easy enough to actually describe the computations. So if I have a matrix, the other thing is a distributed vector is represented by a vector of resources. So a distributed matrix is actually just represented by a matrix of the resources. So if you can do a string, basically a string product for the matrices, these end up being the computations that need to happen out on the cluster, and that's relatively easy to implement. We have a persistence model for distributed data structures. So right now you can think of it as an in-memory database that you can do all kinds of numerical things with. Persistence model is actually pretty easy, because if anytime a resource is updated, it's copied and then written to disk, then you actually have a transaction model, and it's not that difficult to implement. I've started thinking about stringing problems. In particular, I'm interested in feedback problems, which would be easy enough to describe using the current infrastructure. And then the other thing is, I kind of glossed over this before, but the queue scheme with Redis is nice, and it was really easy to implement. In fact, there was almost nothing to implement. It's just listening on queues. The problem is that probably won't scale to, to probably order tens of thousands of queues. In that case, we'd actually need to go to a full scheduler rather than the current scheme. And that's something we would need for if we wanted to really be able to scale it to a really large number of machines. Here are some references for further information. I'm just integrating the asynchronous functionality like this week. It should be done in a week and a half or so. Here's a location for the background package. If you want to see the code that's behind the stuff that I talked about today, it's on GitHub. I have a NIPS paper on this, and you can email me any questions that you have. All right, so are there any questions? Yes?
Do you have any sample code, perhaps comparing with the hello world, the string, the word count sample?
Sorry, can you say that again?
The word count sample is the hello world, the parallel samples. Do you have a version of that implemented in area? Are you considering that?
That does, sorry, which samples?
Word count.
Oh, no, I don't actually. Yes, that would be a good one, especially since a lot of the other work I do is actually with text. So that's another, yes, and that would be a really nice application for sparse or mixed sparse and dense matrices. I don't, that's a really good idea though. And yes, I'll definitely get on that. The matrix stuff is not, is a little less further along, it's less further along than the vectors and data frames. And I probably won't get to it for a couple of weeks, but that's a nice application. Thanks. Yep.
Just for my own education, can you just outline how does a distributed sparse matrix in R look like? I have no idea.
So right, so you have all right. So yeah, so a dense matrix is essentially a vector that we index in 2 dimensions. For a sparse matrix, you usually have they're called you can do they're either column compressed or row compressed, where basically you say you give so row compressed would be you give a row number you give an index where row 1, for example, starts, and then where row 2 starts, and anything between those two indexes from anything from that first index up to where row 2 starts would be columns of the first matrix. An easier way to think of it is basically it's the coordinates of the non-zero elements of a sparse matrix, right? So if most of them are 0, there's no point in me having a big long vector of zeros. It's a much more efficient representation if I basically give you the coordinates of the non-zero elements and then give you the coordinate and then the actual value, since it is the value of the non-zero element.
My question was more about the distributed part of that.
Oh, so for the distributed part, if an entire block is 0, then we can keep track of that on the coordinator side, right? So I could make it an NA, because basically, anything that involves that block, I don't even need to send out to the cluster. I know the result of that 0 block and multiplied by something else.
But you need to store somewhere the information that this block exists and it's 0, which in a non-distributed way you would even know of this block. That would not be memory allocation.
Well, okay, so for the distributed matrix, the actual matrices that are holding the data can be either sparse or dense. The coordinator doesn't even need to know if they are or not. Because if I'm doing something like the matrix or the multiply that I showed at the beginning, what happens is I just pass either I pass. So say one's dense, one's sparse, and in the example that I have, basically I move the sparse thing over, or the sparse matrix over to where the dense matrix is, and do a matrix multiply. R already knows how to do that mixed dense sparse matrix multiply, and so it's handling the actual representation of the underlying data for me. All the coordinator really needs to know is where the resource is.
Okay, so you have the matrix on one computer, not.
Yeah.
Oh. I thought you distributed a single matrix.
Oh, so I think I'm.
Maybe we can also.
Sure. Yeah. Okay. Okay.
So it looks like you're copying data around. Okay. How do you handle stale data when the data changes?
Yeah. So for the example that I showed in the beginning, the convention right now is that once the expression is executed, this would be a temporary object in R, and it would be garbage collected, unless I brought it over explicitly. Now, what you can do is. So your question is basically, what happens if you have more than one B out here, and I want to update one of the Bs? So that has to be handled by convention, right? If I'm going to update B, I need to actually do a broadcast, so that every single one of the Bs is updated. Otherwise, then I can run into consistency issues. So I guess the solution is basically to handle it by convention or policy. There's nothing in the low-level distributed computing framework that precludes you from doing that. So you could run into cases where you don't have parity between distributed objects. But it's easy enough to get around.
What about extending this to GPUs, like not working the cluster locally, but managing like matrix operation in the GPU? Is this compatible already?
So on the GPU, I think. So yeah. So one thing. Yeah. So I guess one thing to note is, and this is related to the representation is, the coordinator is only creating expressions, right? There's nothing in the framework that dictates how this matrix multiplication actually is going to happen. So if I compile R against like the Intel math kernel library, then on that machine it's going to use the math kernel library. So I think for GPU, because R isn't that, as far as I know, it's not tightly integrated enough with the R is not tightly integrated enough that you get GPU behavior with the matrix multiply. But you could change this so that rather than B, times this thing, it could be, it could be GPU multiply A and then pull A. Right. So you could incorporate it. It may require you to change some of the expressions though.
Sorry, another question. The Redis queues, do we have one per worker or one per resource, like data platform?
So each queue identifies a resource on the network. The actual data associated with that resource can be in more than one place on the cluster, right? So that's essentially that redundancy that you get. So if a machine goes down and it has a resource, if it's served redundantly, then you can still handle computations that involve that resource.
But your Redis basically scales with the number of resources in the cluster and not with the number of nodes.
Correct. Right. Yes. Okay. Any other questions? All right. Thank you.